All right. So on the topic of supporting cognitive functions, we have our third lesson here, which is about mental workload and multitasking. Now, in the previous two lessons, we talked about attention and we talked about memory, and I want you to think about workload, mental workload, as the need for using these precious resources, attention and memory. They're in limited supply. And so, as we are using them for various things, as we need them for various things, that's how I want you to think of workload. Okay? Multitasking is about finding a way to distribute these resources among multiple different tasks or multiple different or lines of reasoning. So, mental workload is a very important concept in the field of human factors and human systems topics. So, again, attention and memory. Think of this as how much is required to do something. And think of how much a worker is enduring as far as the demand for these resources. And so this is interesting because if we can measure this somehow, if we can understand the effects of this, then we can make engineering decisions about, how many tasks an operator can handle. How busy are they right now, and therefore how likely are they to, have an overload, have a potential error occur. Can they do additional things, or are they at their limit? And then another key thing to think about is do they have an ability to handle something unexpected? If somebody is at their mental workload limit and something unexpected happens, they're not going to be in a good mental state to be able to handle that. And this is a lot of times how accidents happen. So when you see humans involved in major catastrophes, um, if you can boil it down to, well, look at their workload and could they have handled this if they weren't doing so much at the time? A lot of times the answer is, yeah, maybe they could have done better with it. So here's an example that I think really isolates this idea of mental workload as how much of your attention and working memory resources you need. So these two tasks here, if you were to do each of these mentally, you are doing essentially the same operations, but in one case, you are doing more of them before you get an answer. So you've got a larger number of subtasks. It's going to take you longer to do these mental additions 4 times than twice, or however many. You have more that you have to keep in your working memory as partial solutions in this case. So these are things you got to keep activated in your working memory. You need to rehearse them, maintenance rehearsal, in order to keep them there. And you have to sustain your attention for a longer period of time in order to be able to do that. So this has more mental workload associated with it because it requires more memory, requires more attentional aspects. It's very important, I established right off the bat, that it is not the same thing to say as workload goes up, performance is more and more problematic. Okay, and the example I have here has to do with driving. And I want you to recognize that these are three, I hope you would see these as three very different workloads for the task of driving. Totally open road, maybe normal, traffic in a, not Houston, and then Houston rush hour traffic. uh, Workload is different in these three cases, but performance, if I'm looking at how well can somebody drive, as in performance measures like how well do they manage their speed, how well do they manage, where they are in the lane, how well do they attend to the vehicles around them, it might be really great in all three cases. Performance doesn't drop off necessarily just because workload got heavier. However, if we reach our overload state, so in each of these cases, I'm assuming we have a driver who is well practiced and isn't getting totally overwhelmed by the workload of this scenario. When we do get overwhelmed, and one good example is when we're learning to drive and we have to proceduralize all of these rules and all of these things, we haven't practiced them and made a lot of it automatic yet. It's much easier to get overwhelmed and to overlook things and to then have a suffering in our performance. But only when we reach our overload state, and I'm going to talk about the red line of cognitive workload in a couple slides. Only when we reach that state are we going to have performance drop off. So the relationship between workload and performance is somewhat complex, but you can boil it down to these four general factors that affect performance related to workload. So the first is the arousal level. Now, you may have seen something like this before. You may have heard something about the inverted U of performance, and that refers to this graph here, which we also call the Yerkes-Dodson law by Yerkes and Dodson from 1908. So it's been around for a while. But what this essentially shows is the relationship between now, arousal is an intentionally generic word, but think of this as like mental energy, mental stimulation. Okay. If we get the sweet spot of workload, of stress, of whatever mental energy we're talking about, we're going to get the most performance, the highest performance levels out of the human operator. So again, this is something you might have heard of because like management sciences would look at this. You know, how much work do I give my employees so that they can produce the best? Well, if you give them just the right amount, it's great. If you overwhelm them, their performance will start to drop off. But if you underwhelm them, if you expect less, if you don't have the stress at a certain level, they're also going to underperform, and it has to do with you kind of calibrate your performance to the expectations in a way. But this also has implications for just general performance. So you can even think about driving. As I'm driving in and the traffic gets heavier and heavier, yeah, I might start to eventually have a point where I suffer in terms of my performance because I'm getting overwhelmed. But I also can suffer when I'm really bored. When I've been driving, through Nebraska where I grew up, and it's cornfield, 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 and not a whole lot of visual or mental stimulation, so my arousal levels are low, and I can start to be an unsafe driver because I'm so bored. And I know those of you who are drivers have examples from your own that you can probably relate to. But this is one case where I would argue that the science of doing things while driving. We know a lot about it. It's a lot of our research actually these days. It has to do with the driving world. But safest driving performance might include adding a task. Okay, so think about driving by cornfields, and this is where I would say, hey, this is turn on the radio. Get some more mental energy going there. Have a cell phone call somebody, talk to them, because that stimulation might be what you need to be a safer driver. Now, of course, if you're already kind of working hard and then you add in, let's turn on the radio, let's have a cell phone conversation, you can end up in this zone too, which is not what you want. But this at least illustrates you can have a safer situation by adding mental stimulation. The next factor to consider between workload and performance is this. I alluded to it earlier, this red line of cognitive workload. This is the limit, and it's a theoretical limit, but it has, in practice, you can see its effects. And so imagine the way I want you to use this graph is resources demanded here. This is kind of like the difficulty of a task, or how much I need to devote to do something well. And at some point, I can meet that, so I can give my mental resources to this, and I can do it with, I've still got a lot of capacity here, but at some point I'm going to reach my limit. This is my brain. I don't have any more than my own brain here. So once I give up all my attentional, mental, working memory resources, I'm going to hit my limit, and that limit can be expressed in terms of the resource demand as this red line. This is where I'm going to have a potential problem if a task requires more than this amount of resources. And if you map performance on top of this is just superimposing it. Generally what you'll see is performance doesn't get affected all that much as people approach the red line. I mean, it's going to drop off a little bit. It really depends a lot on the nature of the task. But it doesn't go that bad. So imagine this is driving in really empty road, traffic, maybe getting close to Houston traffic, and then I reach my limit and I can't handle any more processing. I can't give any more resources, and so I'm in overload state, and your performance will have this precipitous drop. It'll be a noticeable drop here. Now, In practice, the way this is identified is generally by watching performance levels, and where it takes its nosedive, that might be okay. Well, there's the limit, there's the red line. That's as much as this driver can handle. That's not really, I mean, that's a useful thing to know, but if you're trying to predict, for example, when somebody was getting close to the red line, that's harder to do without noticing when they've surpassed the red line and they've started to do really poorly in a task. So if you want to detect that a driver is reaching their limit, you don't want to wait until they're starting to crash to go, oh, there's their limit. So some of the research we do in my lab, and I'll show you some slides later that illustrate some of this, has to do with detecting where this red line is by using other sorts of measurement techniques. Okay, so up until this point, I've been kind of talking about resources demanded as, I got to do one task and how difficult is it. But generally, we're almost never doing just one thing. So if we're doing multiple things at once, we're multitasking. We are separating, or we're distributing our mental resources to multiple different things. Okay, so the technical term I want you to associate with this is time sharing. So in the same way you might say, I've got a timeshare in Aspen or Colorado or something, and what that means is there's a building there that you own only at a certain time of the year, and everybody, other people own it at other, it's a joint ownership, but your ability to use it is only at a certain time. You can think of mental resources the same way. So you're going to give some of your attentional resources to driving and some of them to something else, and you're going to sort of share in time when that attentional resource is used on each. Okay. When you can do these two at the same time as well as you possibly can, we'll call this perfect time sharing. And this is when you can do task A, and you can do task A by itself and do pretty well, do task B by itself, do it pretty well, and if you do A and B together, you don't have a noticeable drop-off in performance for either task. So usually something very simple or something really highly practiced, like walking, if you're a frequent walker, and like chewing gum, if you're a frequent gum chewer, then if you walk and chew gum at the same time, you're probably not going to see a noticeable drop-off in performance in your walking or gum chewing abilities. However, when you start combining things that really can't be done equally well together as they can in isolation, like driving and interacting with a cell phone, then I'd say these are probably not perfectly time shareable. And we can study time sharing, and we'll have that in a few later slides here. So if you can assume people are doing more than one thing, and that humans are not helplessly having to do more than one thing, they have the ability to choose which tasks that they decide to allocate these resources to, and that can change with time. So task management is a way of saying, we have power over these resources and we can choose. So for example, if I'm driving and talking on a cell phone, I can at times say, the driving task is getting really heavy right now. I need to allocate more of my cognitive resources to driving and less to cell phone conversation. And so you can, on your call, you can say, hang on, I gotta focus on driving for a bit, or I'm going to call you back, or whatever. These are all examples of task management. You're allocating your resources to one or the other. So we have the ability to do that, but just know that if you have a really complex task management strategy, so if you're talking on the phone and eating a burger and trying to watch something on video and drive, obviously a terrible idea to try to do that. But if you're trying to keep track of, I can do all these things until traffic gets heavy and then I'll drop one or the other, and you have this strategy for task management, well, that strategy itself will break down when you get to an overload state. So maintaining that strategy and thinking about, all right, what should I do as far as these tasks, that's a task in itself. So you want to keep that in mind. And not just like overloading and the resources that get time shared among different tasks, but sometimes the processing that's done for different tasks is confusable. And so just like we talked about, with the display design principles, with documentation, things that are similar can be they get associated, and then they also and whether or not that's appropriate, and they also can be confused. So just to keep this in mind, and it's not just about overloading, but it can also be about swapping things for each other because they are very similar. Okay. So we've seen this before. We've talked about this with regard to display principles and its multiple resource theory. Um, this represents, we're talking about workload and performance because if we think of workload as one pot of soup that represents our mental resources that gets doled out until the soup is gone, that's less accurate. It's really more like we've got a whole bunch of different bowls of soup that do different things, and we can give out soup from multiple different bowls at the same time. Okay? That's a strange analogy, I know, but it basically relates to these mental resources. And if you think about neural structures that are associated with these resources, you can think about neural activity at these locations as you can associate that with one task, but they're not really shareable for multiple tasks sometimes. Okay, so I can have part of my brain active for hearing and part of my brain active for vision, and the two don't really need to compete for the same things. But there are some resources we'll talk about, like memory resources, working memory, where you really got to devote them to one thing or the other, and they're not very shareable. So these resources, they're like pots of soup that you can give out to different tasks in order to get things done. Some of them are more shareable than others. And this is the representation of this theory that I think is best for using it. And it kind of maps out these mental resources with solid lines anywhere where there's a separation of resources. So you've already seen, in this previous one, I've kind of mapped out the senses. And we only have two of them here, but these are the sensory modalities here, vision and audition, are separated by a solid line here for the processing stage of perception. It goes about this deep, and then the processing stage of cognition is all mixed together. And so this is kind of the working memory part. And then our responses are separated again. And basically anywhere you see a solid line means we have a separation of resources. So if you have a task that consumes these resources, and you might say, this is driving, this is where, I need vision, and I'm just making that up, but you can call that task 1, and then here's task 2, and where you can see their overlap, this is where you're going to have competition for that single pot of soup that represents this quadrant of resource, or this three-dimensional space that is that resource there. So some of these resources are shareable, but they get, it's like a timeshare where you got to have a roommate for a week or something, that maybe wouldn't otherwise be wanted there. You'd have a better experience without it. And then sometimes you just, they're not shareable, and like, for example, verbal responses, speaking, you can say one thing at once. You don't have two mouths so that you could speak two different verbal messages at once, right? We have only one set of eyes, and so we can focus on one thing at once. But we have a field of view that could take in several things at once. It just gets harder to share them. All right, so most of the time when people talk about this theory, they refer to this dimension here, the sensory modalities, and the separation of sensory modalities. And we only have vision and audition here because this was built on empirical evidence. So this representation here, this description, is based on the body of research that's out there that we know there's a separability to this. We think also probably, the other senses could be separable as well, but there's not enough research out there to make a really strong conclusion about that. So for the most part, we say vision and audition are the two primary ones where we think of applying this model. And the way we can come up with solutions here is to say, okay, we know if we can separate the sensory channels involved in a task, that people can do more of them together. They can timeshare more effectively. And so that's another principle behind these, what we call multimodal interfaces, where we have multiple sensory channels engaged. And the smartphone is a great one here because I can access what I need visually or auditorily. I can input what I need either by touching it or by speaking into it, and that's beneficial because if I'm in a context, where I've got these resources consumed, and I have the ability to use either vision or audition to perform what I need, then that allows me an option that is relatively under demanded, right? So there's relatively less demand for one resource than the other, vision or audition. So I can distribute the load across my senses a little bit more evenly. So that's the idea with these. So multiple senses engaged. All right, so that's sensory modalities. The other one that I really want to highlight here has to do with our working memory processes again. So lesson 7.2, we talked about working memory, and we talked about two subsystems. And so if you want to recall those, one had to do with imagery, mental imagery, the visual spatial sketchpad, and the other had to do with linguistic energy, sound energy, and the meaning of that. And so that's our phonological store. And those map very nicely to these processing codes in Wicken's multiple resource theory model. So spatial processing has to do with where things are, has to do with imagery, has to do with very much with our mind's eye. And verbal or symbolic processing, this is really about the meanings of things. So when we talk about symbolic and pictorial processing, symbolic and pictorial elements in a display, the symbolic aspects are processed with this processing code. What is the meaning of those words, of that symbol, of that icon, and the where and experiential sort of aspects of it, like looking at a map and determining where things are relative to each other. That's using your spatial processing code. So a couple of ways to think about these two. Now, almost every task we do involves each of those types of memory. But there are some tasks that maybe load those processing codes a little bit more so. So think of navigating in a city. You're driving, you're trying to figure out where am I going. When I say where, and I think of imagery, and I think of locations as like an image in my mind's eye, I am using my spatial processing code. If I'm reading language, I've got a paper, or you're reading the words on the screen right here, that's obviously verbal processing code. Speaking, I'm generating language. I'm creating a message in language, so I am using my verbal processing code there, and that's drawing something that I see. So I'm trying to I'm looking at something and trying to recreate it in an image. That is very much an image processing sort of thing, where things are, where they are relative to each other. Drawing a picture. But maybe what I am drawing has symbolic content to it, So I think about the meaning of this thing I'm drawing, that symbol there. And so that's verbal. So I don't want you to get mixed up and think verbal is only written language. This is anything that's symbolic, that has some meaning that we've had to learn at some point, that we've had to associate, with a code. So that symbol is, interpreting that symbol is verbal as well. Throwing a ball or catching a ball is very much spatial, okay? And this is because we are very much using our spatial processing to determine where we have to throw something. Where will that receiver be? Where will the ball be when it gets to me? How will it feel? You're thinking through an experience. You are using your mental mind's eye as much as you can, and so that's spatial. Also, recognize that the spatial processing code, if I go all the way up to the response stage, that is a manual activity. If I'm performing a manual response, that means manually using my hands or using my body in some way in to move, like to throw a ball. That is very much using the spatial processing code. This one's tougher. I want you to think about this for a minute. So let's say you just went out to lunch and you're trying to figure out how much change do I leave, for a tip from my waiter. And that is what now, spatial or verbal? And I say it's a little bit of both, but I would call it a verbal example if you're doing the mental math, because you're doing symbolic processing and you're having to, multiplying and, coming up with rules. I tip 20% or whatever. These are all stored symbolic sorts of messages, and you are applying these rules in order to come up with your answer here. Now, you may imagine in your head what it looks like when, you may think, okay, I want to pull out two $1 bills, and then you can imagine in your head what a $1 bill looks like, and you can use your spatial working memory to retrieve that, to make sure you get the right things out. But in calculating how much, that would be verbal. Where did I leave my keys? So if you think, where was the last place you saw them? When you say that, you're creating in your mind's eye, the mental image of seeing the keys. Very much a spatial example. And here's several others that I want you to think about, but I'm going to just zip through them here and talk about a couple of key ones. And let's say I'm talking on a cell phone, and I may have a conversation that is, hey, what are we going to have for dinner? And that's going to be mostly a verbal or symbolic conversation. But if it's, if I'm driving or something and you say, okay, well, how do I get to that restaurant? Or where is that place? Well, what and where are both part of the conversation. They're both part of now the mental processing that has to go on. So I'm using a little bit of my spatial working memory, my spatial processing code, in imagining where that restaurant is, imagining the storefront of that restaurant, or where it is in town, or even getting instructions to a place you haven't been before. Somebody could say, it's by the mall, it's across the street from blank blank. What you're doing is then recreating the mental image in your head, and so you're using some spatial processing. I like this example too, a football game or any sports play-by-play. And a really good sportscaster, if you're listening to a radio, a really good sportscaster will say things like, the Aggies are moving the ball left to right across your radio dial. And, at first I'd think, well, what is that? Left and right are meaningless to me when I'm riding in my car and listening to the radio. That doesn't mean anything. But what's going on is a really good sportscaster is watching and they're translating their visual experience of watching the game into a language that allows you in your car to recreate that visual imagery. So they're giving that level of detail left and right because they are telling you what they are seeing as they see it in a way that allows you to recreate that same imagery. Editing a report, probably you're familiar with the how do I say this in fewer words, but you may also have dealt with the how do I say this in fewer words and less space, right? And so if you think about, I need to state this without going over that additional line because I'm at my page limit, then that's you're thinking of the spatial properties of language as well as the verbal properties. So, on the concept of multiple resource theory, this is an interesting application of it. And you could say, I've got two tasks, and driving and doing one of these other things, either reading a newspaper, talking about what to have for dinner, or talking about how to get to a restaurant. And which of these is going to be more problematic? I don't know which ones are okay and which ones are not okay, but what I can do is tell you which ones are worse to try to do together. Okay? And so if I map out these dimensions of the multiple resource theory cube, so if I take this, if I take these and I block out each of those spaces according to the resources that can be consumed, I list them out in a table form like this, then I can say, okay, I've got newspaper. So let's say driving is going to require mostly my visual sensory channel, mostly my spatial processing, but a little bit of auditory and a little bit of verbal because I'm reading signs and I'm listening for things like sirens around me and car engine noises. The way that I control this task is only manual responses. I'm only using my hands and feet to control the vehicle. I'm not using voice recognition to control the vehicle. And maybe a newspaper task is also visual, is also a little bit spatial and a lot verbal, and also maybe if I'm holding a newspaper, it's manual. And talking on a cell phone is mostly I'm listening, Mostly I'm speaking a verbal, I'm creating verbal language, and I'm processing verbal language. But in one case, where is dinner, I am also requiring a spatial processing element to it. So what you can do then is look at the cases where we have the same resource strongly required for multiple tasks. So I can see, because I need vision for driving and newspaper requires vision, I've got a bad interaction here. I've got a bad competition for that resource there. That's potentially problematic. I also have a competition for my manual resources with the newspaper. You could look at, what these other two here, and maybe the what's for dinner conversation has very little overlap with the resource demands for driving. So you could say, okay, this is our best option here. Where is dinner is maybe going to interfere a little bit more so than what's for dinner, because it's requiring some of my spatial processing codes resources that are also needed for driving. So how do we use this here? Multiple resource theory. You can apply this if you have a context where you're trying to decide, okay, maybe I'm driving. I know that requires vision, it requires my spatial processing code, it requires manual resources. So if I'm going to add a new task to this domain, which resources are relatively available and that I could make use of in a new design? So manual or voice control, spatial or verbal display. And before you say, well, how would I translate something, between those? Well, here's a good example. If my task is get from point A to point B, I can display it in a way that very much loads the spatial processing code like this. And it could be visual in a map, or I could have verbal and visual, or verbal and auditory. So these could be, I could have a sequence of spoken instructions that also help me get where I need to go. It would still be a display, but we'd be engaging different resources. And I'm not saying one or the other is necessarily better, because there's a lot more at play here. Like, for example, this is a much better tool. The map is a much better tool for if I get a little bit lost than a sequence of verbal instructions. But in any case, you can think about the processing resources that are consumed in either case. Okay, so if we have multiple tasks being performed, we need to find ways to keep that below the cognitive red line, and if we're close to or exceeding that, then we are in overload states. So how do we address that from an engineering perspective? We can redesign the task or redesign interfaces that are used for the task to reduce the overall resource demand, or to redistribute them more evenly, the demands across different resources. So we may end up, translating some displays to be able to be accessible to other resource channels. If you train people, some of these things, like driving, for example, they're not as hard as we get lots of experience with them, because they become more and more automatic, more automatized. That's the key word here. And so then they're easier to timeshare. So it becomes more like walking and chewing gum if you're highly practiced. We can use external memory aids, attention directing cues. We can use ways to support these cognitive resources of attention and memory with external tools. So some smart interfaces can make use of that. Task management, deciding which task to attend to when, how much resources to give to each when. That can be supported with tools and as well. And then find a way that if you have to do two things at once, and that's the problem, find a way that you could do them in sequence. And so very easily, if you can't drive and text at the same time, which you shouldn't, you can drive and then stop and then text. All right. So there's a lot of ways that we can assess workload, and some of this is in the research realm, but this can be done in the industrial realm too, in the workplace. So performance measures, that's the primary way that we'll do this in the research world. Physiological measures are pretty interesting. I'll talk about those a little bit. And then most standard, I think, are subjective ratings. How hard are you working right now on a scale of 1 to 10? Performance-based measures. We have a couple of main methods. And one is called the primary task, and the other is called the secondary task technique. So primary task, like driving, basically this says if you are doing worse, performing worse in something, it means that your workload is heavier. So this is only the case when we are at or above the red line, however. So this is not a great method because of that constraint. Because we can drive in really easy conditions or in medium conditions, and my performance in the primary task of driving won't change all that much because I haven't reached my red line yet. Secondary task performance, this is kind of, it's confusing, but it's really, really smart, I think. So this is where we use a second task that's usually not really a very meaningful deep task, but it's kind of something that soaks up the rest of our resources in a dual task setting, so we can determine how much is needed for the primary task. So this would be like if I'm driving and I go from really light traffic to moderate traffic, well, my driving performance in primary task isn't going to change all that much. But if I have a secondary task on top of that, so that this task could be something like count backwards by sevens from 1,000. And it's a mundane task, but it's just enough to occupy the rest of my resources that I have available after I'm devoting what I need to drive. Okay, so if driving in a light workload scenario or a medium workload scenario doesn't translate to performance differences in driving, it could translate to performance differences in this secondary task if you assume that as the traffic gets heavier and heavier, I can devote less of my reserve resources to this counting backwards task. So I'm going to do worse at the counting backwards task, and that's an indicator of the fact that the driving got harder. So we use performance on the secondary task to infer how much workload the primary task is taking up. Okay? You can also do some very much qualitative sorts of assessments, like talking through tasks. See how deeply people have encoded things. You can get all kinds of different performance measures that way. But the drawback here, we say the Heisenberg principle, which is at least I think it's the Heisenberg principle. It's the if you observe something, it will change. So if you're observing somebody in a task they're performing, they can by nature be affected by that observation, and it's not as natural. So just be aware of that. This is interesting stuff, physiological assessments of workload. This is a lot of the research we do, and I'm just going to give you a high-level description of some of the main ones here. And so we use this in research, but you can imagine ways that this could be used in real-world contexts, and like in work contexts. Heart rate tends to go up as workload increases. Heart rate variability, so this is like your heart rate will change how it beats, the regularity of the beats, and this is an indicator of workload in a couple ways. So we can see accelerations and decelerations in heart rate as there are events, so that's one way that we can look at heart rate variability. But also when people are fully relaxed, your heart, because of the way that your breathing works and your sympathetic nervous system works, as we are breathing in a very relaxed state, your heart rate will change beat to beat just based on when you're taking a deep inhale breath and you're oxygenating your circulatory system. Your heartbeat will speed up just a little bit just during the inhale. And then as you're exhaling and it's consumed the oxygen, your circulatory system has consumed the oxygen, then your heart rate slows just a little bit, and this speeding and slowing becomes much more observable in variability when people are fully relaxed and they're breathing deeply. So we can get an indicator of workload as the persistent so the variability of heart rate over a long period of time it'll get very regular when people are under heavier workload because they're breathing more in a controlled fashion. Your heartbeat tends to synchronize a little bit more, so it's not so lackadaisical. Galvanic skin response, GSR is sometimes called, or skin conductance is another term related to this. And a good example here are polygraph tests, but we use these for all kinds of experiments as well. So what happens is when you have a stressful event like telling a lie when you're trying to tell the truth or trying to get a lie by somebody. That tends to be a stressful thing for most people, and so you have a response called the sympathetic nervous system. Your sympathetic nervous system arousal goes up, and this affects heart rate as well as the perspiration in your skin. And so certain parts of the skin are very reliably, you can detect the current that would, a very, very low current, but that could travel across the surface of the skin. And as you are more stressed, you have more sweat in the surface of the skin, and so there's more conductance of that current. And it's a very fast response. So what you're seeing here, being denoted here in this lie detector test, is it's very likely the skin conductance, and that would spike when we have sort of a stress reaction. Pupil diameter is one we've talked about with vision before, and its effects. It's affected by emotion, as we remember. We can use this to infer workload as well. When somebody looks at something and is trying to extract more detail from it, or it's confusing, the pupil will dilate just very slightly, on the order of 0.1 millimeters. So it's very difficult to measure because the amount of change here due to ambient lighting is considerably greater than this. So you have to be able to isolate workload changes in pupil diameter from lighting changes. Visual scanning, so when people, if you have an eye tracker, for example, and you're seeing where people are looking, it's not really a physiological measure, but it's a behavioral measure here. But people will look at something and dwell on it for longer periods of time when things are confusing. So that's a good indicator as well. And there are several other methods that have been used, that we've used or others have. Generally, they're more expensive than these things. So we're talking about like functional magnetic resource imaging, fMRI, blood flow of the brain, EEG, electroencephalography is electrical activity of the brain. I forget ERP something. It's also electrical activity though. And functional near-infrared spectroscopy. These are all things I've had experiences with several of these, but they're generally requiring a lot more scientific knowledge in order to interpret them, and we use in our lab a lot more lightweight sorts of assessment ways. Just some pictures here from our lab work here. It's one of my PhD students here with the pupilometer she's wearing. We also have oculography. So what you see here around her eye are electrodes that are detecting eye movement, and eye movement is one of our indicators of workload. Here's our GSR system, our galvanic skin response. So we're getting skin conductance across the skin there. This is an example of a thermal imagery method that we're working with some collaborators on. We can detect changes in sympathetic arousal based on heat patterns in the face. This is me wearing a functional near-infrared spectroscopy device, so I was getting blood flow to my frontal cortex here, and that's one way we infer workload. We did that in a flight simulator here. Here's our EEG system. It's a toy, but it's getting frontal lobe electroencephalography. That's also this guy here. And we do a lot of tests where we're doing multitasking, and we're trying to see, performance-based measures, how well do they synchronize with physiological measures. So we did some pretty cool stuff. I love this topic, these sorts of research activities that we do here. Okay, so that's physiological measures. We talked about performance-based measures, and then the last one is subjective methods for assessing workload. And these are the most common. You've probably dealt with something like this in the last month or so at least. Any sort of scaling, we call Likert style scaling, if it's translating words like strongly disagree to strongly agree into numbers. And a good number of elements is 5, 7, or 9. 7 because 7 plus or minus 2, that magical number. So people can think of 7 as they can distinguish 7 things. That's generally makes sense. Plus or minus 2. And having an odd number is nice because it causes a forced choice. You don't have like the completely neutral, or you can. I'm sorry. Odd does allow a neutral response. So 1 to 5, where 3 would be I neither agree nor disagree. So if you need somebody to have a forced choice, then you probably want an even number of elements. One thing to think about is the distance between successive elements. So how do I go from 1 to 2? Is that the same distance in a sense as from 2 to 3? So you assume them to be equal. In practice, a lot of times people assume, you might see that people would map it out in a way that doesn't completely support this assumption. Beware that you can mix the valence of questions. I've been burned by this before, and I'll show you what I have my example here. So the valence is like the positivity or negativity of questions. So if I'm going strongly disagree, strongly agree, make sure that that also matches up with if I feel a certain way in general about something, it tends to align and it doesn't switch. And so let me show you that example on the next slide. Couple of biases in human responses to be aware of. People tend to stay away from the extreme values. So, I got to save something from answering a 1 or a 5 or a 9. The most extreme values are like, that's as much as I can imagine. So they tend to go towards the center. People can be very much affected by how a statement is presented. Do you strongly agree with this or not? Or you can phrase things in such a way that leads people to certain responses. That's a very difficult thing to try to have a neutral question for some of these surveys that we work on. And then social factors, if you're getting a subjective assessment and it's coming from the boss and it's asking about the workplace and somebody's going to look at it, it's harder to get an objective measure. Okay, so this valence of suggestive questions, here's my successive questions, my example here, and I've been gotten by this one. So the instructor is fair and consistent in grading. Strongly disagree, strongly agree, 5. Instructor seems to care about whether or not I learn their material. Yeah, he's great. Dr. F's great, 5. Instructor is difficult to meet with outside of class. Yeah, he's great, 5. Oh, so here's what I mean. So the valence, if you like something, and again I'm saying me, but it can be anything. Oops. My pen's not working, is it? No, it's not. Okay. Pen's not working, sorry. Okay, never mind. So if I were to circle 5, 5, 5, and what happens here, and this happens with this really has happened to me with, come on, get out of here. Okay, sorry about that, I can't figure this out. This has happened to me where the questions, in order to answer in a positive way, you may have 5, 5, 1, 5. And people are they kind of get in a mode and, top-down influences here. Think of what we've talked about with documentation. Top-down influences, I'm going to be less expectant that I'll have to answer a question in the opposite form. So I start to associate strongly agree with strongly good. And I can get mixed up in this way. So beware that. Okay. So a couple of standardized, I'm going to end on a couple of standardized ways that workload has been assessed with standard indexes. The Cooper-Harper scale is something that was originally created for aircraft handling. And so it comes up with a rating of a pilot from 1 to 10, and these numbers are brought at after essentially asking qualitative questions. So how well does a pilot control an aircraft has to do with all of these questions, and if you can follow this flow chart and answer these questions just such, you end up with a numerical rating. So it's translating what's otherwise a bunch of descriptors into a single number in a pretty effective method. And similar sorts of flowcharts like this have been used with the Cooper-Harper scale to come up with workload ratings on a 1 to 10 sort of or similar scales. There are different methods that we've used in the lab of really simple to relatively more complex multi-dimensional sorts of workload assessments. So it's not just 1 to 10, how hard was it, but it's 1 to 3 for how much does this affect your load over time, how much is your mental effort going in, what's the stress. So the SWOT, subjective workload assessment technique, has those 3 dimensions. The NASA Task Load Index, this is probably the most widely practiced one, the TLX, NASA TLX. And this has 6 dimensions. And this is actually a screenshot of the survey that we will use in our research a lot. We'll actually print off sheets with this on it. But mental demand, physical demand, temporal, performance, effort, and frustration. And the way that you would do this is you'd give somebody this after they've performed some task, and they rate it however they will. And this can be like an analog scale that can exit anywhere. You can interpret these however you want, but they'll X them here. Put an X on there. And then we have to figure out, so whatever these mean to the person being surveyed. So you may be looking at this now and saying mental demand, physical demand, what do these really mean? How are these different? How is effort different from mental demand? And the answer is it doesn't really matter as long as you are interpreting it in a consistent way. So if you're having a hard time interpreting multiples of these, it's okay. The way that you think of it, you answer that way. And then we go through a process of determining, well, which of these dimensions do you think contribute more so overall to your overall assessment of workload? So, in your opinion, which contributes the most? And you do pairwise comparisons. And there are these 6 categories, so there are 15 total pairings of them. And if you answer this question 15 times, with each pairing, you end up with a tally for each one that wins, and then you count up those tallies, and you have a weighting of 0 to 5 for each of these dimensions. And then you simply multiply this value, however you translate that. So this could be on a scale of 1 to 20. I think there are usually about 20 of these. So you could say that's 1, 2, 3, 4, 5, 6. So that's a 7. And then you multiply it by its weighting that you just calculated by the tallies, and you sum them up. And that's how NASA TLX comes up with a single index, a single number that represents the workload of a certain experience. So that seems like a lot, but in practice it's actually pretty fast to go through this, and there are a couple of software devices that can make it even faster. If you want to learn more about this, you can check it out, or you want to do this, apply this to something like your semester project, for example. You can find the full instructions for how to do that at this link right here. That's it for workload.